RC circuits are what we call any circuit with a resistor and a capacitor in them. But before we get to those, I wanted to briefly look at doing a Kirchhoff loop rule when you have more than one battery in series like this. So if we go ahead and loop around in the direction of current, so I'm going to loop around in a counterclockwise fashion, the equation we could write, if I start here at A, I'm going to have 20 for that first battery. Now the second battery is facing the other direction, so I'm going to subtract off 12 minus the voltage drop across the resistor, which is going to be whatever I is times whatever R is, and that will all equal to 0. If I made the loop the other way, still having my current go this way, and I start at A, I'm going to go across my resistor, but now it's going to be a voltage increase since I'm looping in the opposite direction of my current. So I'm going to have I times R. And then when I go across this battery here, I'm still going from the lower potential to the higher potential. So I'm going to call this a plus 12, but it's not because I'm going in the direction opposite of the current. It's just because I'm going from the low potential to the high potential, and I'll do the example if we assume the current is the other way to make that a little more clear. Then when we cross this battery, we go from high potential to low potential, so we have a voltage drop. So we obviously get the exact same equation, just multiplied through by a -1, which doesn't change anything. But what I wanted you to see is if we assume the current is going the other direction, and then we still write these same two equations. So let's start at A and loop around counterclockwise. We're still going to get 20 volts. Okay, so it doesn't change direction, it doesn't change sign because I changed the direction of my current, as opposed to resistors that do. Okay, now I'm going to go across my 12 volts here, and since I go from high to low potential, that's a voltage drop. And then when I go across my resistor, now I'm going across in the opposite direction of the current, because this current looping this way would eventually come up and be going that way. So we're going to have plus IR equals 0. Now if I loop in the direction of the current, so now I'm going clockwise, and I'll start here, I go around here, I'm going to have a voltage drop, so negative IR. Then I come around here, I'm going to go from low potential to high, so I'm going to say plus 12, and then I go high to low, so minus 20. And once again, I get the exact same equation, just swapping positives for negatives, which is what I want. But once again, the point is to decide whether your voltage drop, whether it's a drop or a gain, it's whether you go high to low potential. It has nothing to do with the direction that you assumed your current was going. Now these equations aren't the same as these, and that's because when we solve these equations, we would get a negative current, negative value for our current out, which would tell us that the current's actually going the other way. And we know that because this battery would be pushing harder than this battery, essentially. Okay, now when we have batteries in parallel, we always want them to have the same voltage. And the reason for that is if they have different voltages, essentially they're going to be pushing current around this little parallel loop here, trying to equal out the voltage, and you're going to drain one battery and try to charge another battery that might not be rechargeable. So this is one of the reasons why they always tell you to put in 2 new batteries, because if you put in a new battery with an old battery, that old battery is just going to drain the new battery. But we do put them in parallel at times because this is going to allow you to get more current out of the battery setup. But we also put them in series plenty of times as well to increase the voltage, and in that case you still want them to all be new batteries. Alright, on to RC circuits. So if we have about the simplest RC circuit we can imagine here, where we have a single capacitor and a single resistor, and then we have a battery of EMF E, and then when we close that switch, if we think about what's going to happen, well, this capacitor is going to slowly charge up, and we can write equations for expressing the state of the charge and the voltage and the current of this circuit at any moment in time as it's charging. So we'll start out, we're going to derive these equations. We'll start out doing a Kirchhoff loop. So if I assume that the current is going this way, away from the positive side of the battery, and then I make a Kirchhoff loop, again looping in the direction of the current, because why not? I'm going to start out with my EMF here. Now as I cross the capacitor, this is something we haven't really dealt with a Kirchhoff loop yet, I'm going to get a voltage drop, because as that capacitor charges, it's going to build up positive charge here and negative charge here, so it essentially acts like a battery facing the other direction. And the voltage on a capacitor is Q over C, so I'm going to have minus Q over C, and then I go across my resistor, so we get a voltage drop of negative IR on that resistor. Now if we do a bit of rearranging, we'll get that this all equals 0. So we get the EMF is equal to I times R, and if we replace I with dq dt, we're going to get R times dq dt plus Q over C. And then here what we want to do is a separation of variables, so we can start out by saying E minus Q over C equals R dq dt. Then we can get EC minus Q over C, just putting everything under a common denominator here, dq dt, and moving right along we can have a dq over here over EC minus Q. Essentially we want to get the Q and the dq on the same side, and then we'll have dt over here over RC, and then if we integrate both sides, this guy from 0 to Q, because we're saying Q is the charge on the capacitor, and this guy from 0 to T, we'll end up skipping a few steps, natural log of E times C minus Q all over E times C for this side, and we'll end up with a negative T over RC on this side. And then if we take e to the power of both of these, we can get 1, and we simplify that a bit too. 1 minus Q over CE, my e became an epsilon for some reason, equals e to the negative T over RC, and now we're just about there. I'm going to jump back up to the top here. If I solve that equation for Q, I'm going to get Q equals capacitance times my EMF times 1 minus e to the negative T over RC. And there, my friends, is a nice equation that tells us the charge on the capacitor as a function of time, and it depends on the EMF of the battery, the capacitance, as well as the resistor that we have in series there. Now if we move this C and divide both sides by C, and we've got Q over C, then this expression becomes the voltage on the capacitor, and it looks very similar to the other expression. And the last equation we want is the current of the circuit as a function of time, and the current is dq dt. So we take the derivative of this guy up here, and we'll end up with E over R times E, different E here, T to the RC. Okay, and you'll notice we've got this RC term coming up a lot. A lot of times we'll rewrite these equations with a tau in place of the RC, and this thing is called the time constant. And I'll talk a little bit more about that later. So if we were to graph what was going on with our voltage and our current as a function of time, our voltage would start out at 0 because we have an uncharged capacitor. Again, this is the voltage across the capacitor, not the voltage on the battery. We're assuming that's constant. That voltage on the capacitor is going to increase until it asymptotically approaches the battery voltage, at which point you would have like two batteries in opposite directions that have equal voltage, and no current would flow. The current, on the other hand, will start out as a maximum because there's no resistance due to the capacitor to current flow. And then as that capacitor gets charged, then the current will drop off asymptotically to 0. All right. So if we summarize all of those wonderful equations, here they are, where we sometimes put a subscript C here to remind us that this is the voltage on the capacitor, not some other location in the circuit. So let's do an example. We're given a number of values here for our RC circuit, and then we've got to find all kinds of things. So for part A, we just want to find the time constant, that's tau. This is nice and easy. It's just resistance times capacitance. So 20 kiloohms times 0.3 microfarads, and that works out to be 6 milliseconds, 6 times 10 to the negative third. And the time constant is a time, and it's measured in seconds, even though these units look kind of strange here. You've got ohms times farads, right? That does work out to be seconds because ohms are equivalent to volts over amps, just from V equals I times R, you can see that. And then farads from Q equals CV, you can see that this is equal to coulombs per volt, so the volts go away. And then you've got coulombs per amp, and amps are equal to coulombs per second, so those cancel, the second comes up top, and so yes, these are units of seconds. For part B, we want to know the maximum charge, and so if you look back at our equation here, well, the maximum charge is when t gets large, this term goes to 0, so you just have 1 times this. So C times E is going to give us our maximum charge, so I'll go ahead and write that. Qmax equals the capacitance times the battery voltage, which again is a nice simple calculation. 0.3 times 12, which gives you 3.6 microcoulombs. Part C, the time it takes to reach 99% of the maximum charge. So we want Q to equal 0.99 times Q max. Well, if we compare this equation to our general equation for Q, which says that Q equals, I'm going to go ahead and call it Q max here instead of CE, times 1 minus e to the negative t over RC. Well, then essentially we want this stuff in parentheses here to equal 0.99. So 0.99 equals 1 minus e to the negative t over RC. And then we go ahead and solve that guy for t. You'll end up with t equals 28 milliseconds. That's the time for that. Part D, the current when the charge is half of its maximum value. Now there's a couple of different approaches here. You could use this equation and set the stuff in parentheses equal to 0.5, solve for t, then plug that t into your equation for I as a function of time. So you could then plug that in here and solve for what the current is at that time. But there's a little simpler way. We know that the Q is going to equal half of its maximum value, and we know the maximum value is 3.6. So Q is going to equal 1.8. And then we can also say that the current is going to equal E minus V over R. This is just V equals I times R, where we're taking V as the battery voltage minus the voltage on the capacitor. So it's kind of like the net voltage here equals I times R. And then if we divide that across, we end up with this expression here. And we already know the value of E and R, but we can find the value of V pretty simply just by taking Q over C, because C is constant, so if I know Q, then I can also find V. So we've got 1.8, this is micro coulombs, so 1.8 microcoulombs over the capacitance, which was 0.3 microfarads. So we know that the voltage on the capacitor is 6. Battery voltage told us was 12 minus 6 all over the resistance of 20,000. And this works out to be 3 times 10 to the negative 4th amps. Okay, moving right along on this multi-part problem, let's squeeze E in maybe right about here. E wants to know the maximum current. Well, the maximum current is going to be just when V here is equal to 0. So that's going to be 12 over 20,000, which works out to be twice what this is. So 6 times 10 to the negative 4th amps. And the last part, we want to know the charge Q when the current is 0.2 times its maximum value. So we can find that current, 0.2 times the maximum value that we just looked at. And that's going to give us 1.2 times 10 to the negative 4th. And we want to know the charge. And so we can again use this expression here, not with V equals 0 this time. And if we rearrange that, we can get V equal to the EMF minus IR. The EMF is 12. We just found I here, so 1.2 times 10 to the negative 4th. And the R value was 20,000 ohms. This all works out to be 2.88 times 10 to the negative 6 coulombs. So as usual in physics, there are a number of different ways that you can approach solving these types of problems. Alright, now once a capacitor is charged, you could hook it up to something else and discharge it, which is what we typically do because we charge it so that we can use it. When we discharge it, we can rederive equations in the same fashion that we did for charging it, and we will end up with these equations here. This time the voltage is going to decrease on that capacitor instead of increasing on it. The current, though, is still going to decrease. So I'll do a little current chart here. Current time is going to decrease. So the current decreases charging and the current decreases discharging. And let me show you a little bit how that works. If we jump over to our favorite little circuit construction kit, you can go to FET and play with this if you would like. So here I have a circuit where I've got a battery, a switch, a capacitor that's initially uncharged, a resistor over here, another switch, and a light bulb. So when I throw this first switch, nothing is going to go on up here because this is essentially an open circuit. But we're going to charge our capacitor here. Here I've got a voltmeter that's going to be graphing the voltage on my capacitor as a function of time. And here I've got an ammeter that's going to be graphing the current in this bottom circuit here. So as we would expect, the current starts out at a maximum value and slowly decreases down to 0 as this guy charges. The voltage, on the other hand, starts out at 0 and slowly increases until it equals the battery voltage. The battery voltage is 10, I'm assuming here. Alright, once we have that capacitor mostly charged, we can go ahead and open this switch, or just drag our wires around, whatever. Alright, we'll open that switch. So that doesn't discharge it and until we close this switch here. So here, when we close that switch, again the current follows the exact same shape. It starts out at a maximum and goes down as we deplete the charge available on our capacitor. Here the voltage does the opposite though. It starts out at its maximum value and then it slowly goes back down to 0. One last thing I wanted to mention, I said earlier that I would come back and talk about this time constant idea, is if we look at when t equals tau, or t equals 1 time constant, in that case we're going to have e to the negative 1, and that would work out in both of these equations here, where you have 1 minus e to the negative 1, as giving you 63% of either your maximum charge or your EMF. And so the time constant is the time to charge your capacitor to 63%. If you're looking at the current situation where you plug in RC here, you're going to get e to the negative 1, and that's going to be the time for your current to drop down to 37% of its maximum value. So a couple of different ways of looking at that. Typically these RC values are pretty small, often in the millisecond range, and even though it looks like it might take a while to get up there, once you're up to about 4 time constants, if you go ahead and plug that in here, you're going to be at 98% charge. So even though it technically takes an infinite amount of of time to charge, it doesn't take that long to get really close to your maximum value. Okay, that's it. We'll see you next time.